Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we'll be dealing with the fourth chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Moving Charges and Magnetism. Let's look at our first question. An electron moving with kinetic energy 6.6 into 10 raised to minus 14 joules enters in a magnetic field of 4 into 10 raised to minus 3 Tesla at right angles to it. The radius of its circular path will be nearest to A 100 centimeter, B 75 centimeters, C 25 centimeters, D 50 centimeters. How do you solve this question? Well, let's write down the given values. Kinetic energy E, which is equal to half mv square, is given as 6.6 into 10 raised to minus 14 joules. And the magnetic field B is given as 4 into 10 raised to minus 3 Tesla. And since the particle that's shot into the magnetic field is an electron, we will know that the charge of an electron is 1.6 into 10 raised to minus 19, and its mass will be equal to 9.1 into 10 raised to minus 31. So these are the quantities that are given here. So we know that the electron is a charged particle. So when a charged particle enters a magnetic field, and in this case it's at right angles to it, so it's perpendicular, then the charged particle ascertains a circular path. It follows a circular path in the magnetic field. So in this case, when the electron is in a circular orbit in the magnetic field, then the magnetic force is equal to the centripetal force required to undergo circular motion. So in this case, QVB sine 90, the reason why 90 is because it's perpendicular to the magnetic field, will be equal to mv squared by r. So therefore, sine 90 will be equal to 1. So QVB is equal to mv squared by r. One of the v's gets cancelled. So r will be equal to mv divided by qb. And we're asked to find out the radius of the circular path. So this is the formula that we should be using. However, you notice that we haven't got specific values of m and v. It's over here that we use the quantity of energy. So E, which is equal to half mv squared, is equal to 6.6 into 10 raised to minus 14 joules. What we do is we now multiply and divide by m in order to get half m squared v squared divided by m. The value on the right hand side would still stay the same because we're multiplying and dividing one quantity, which gets cancelled out. So the quantity on the right hand side would still be the same. Now what we do is we keep m squared v squared on the left hand side, and everything else is taken to the right hand side. So m squared v squared will be equal to 2m into 6.6. So 2m into 6.6 into 10 raised to minus 14. Now let's apply the square root on both sides. On the left hand side, square root of m squared v squared will be equal to mv, while on the right hand side it will be 2 into 9.1 into 10 raised to minus 31. This is the mass of the electron, times 6.6 into 10 raised to minus 14. And all of this is under a root. So now what do we do? Firstly, we'll multiply 91 by 66. So we'll multiply 9.1 by 6.6. So 1 times 6 is 6. 9 times 6 is 54. 1 times 6 is 6. 9 times 6 is 54. And you'll get 6, 0, 0, 6. So we have 600.6, and now we multiply this by 2. So it'll be 12, 0, and then 12. So we'll have 120.112 into 10 raised to minus 45 under root as the answer of MV. So now we got the value of MV. Let's apply this value in the equation. So R is equal to MV divided by QB. So that'll be 120.12 into 10 raised to minus 45 divided by, this is under root, and then it's divided by 4 into 10 raised to minus 3 into 1.6 into 10 raised to minus 19. So therefore, let's convert 10 raised to minus 45 into 10 raised to minus 44. So we have to multiply by 10. So when you multiply by 10, you get 1201.2 into 10 raised to minus 45 divided by it's under root, and then it's divided by 4 into 1.6. That's 4 times 16 is 64. So 6.4 into 10 raised to minus 22. So the whole root of 10 raised to minus 44 will be 10 raised to minus 22. And the square root of 1201.2 will be approximately equal to 34.6. And now 34.6 divided by 6.4 into 10 raised to minus 22 divided by 10 raised to minus 22. So these two gets cancelled. So we have 34.6 divided by 6.4. Let's start dividing. 346 divided by 64. So therefore, so we can convert this into 346 divided by 64 by multiplying 10 on both sides, numerator and denominator. So if you multiply 64 5 times, you'll get 6 times 5 is 30, 30 plus 2 is 32, so you'll get 320, which is the closest value. So minus 320 gives you 26. So now 26 is less than 64. We put a point, so we get 260. 64 times 4 is 256. So we'll get 4 in the end. And then we have to multiply 0, etc. So this division will go on. However, the first 3 digits that we get is 5.40. So this is 5.40 meters. So when you multiply by 10, you'll get 54 centimeters. So that is close enough to 50 centimeters. So we're asked to find out the approximate value. So in this case, the approximate value will be option D, which is 50 centimeters. And that we found out by using the relation between centripetal force and magnetic force when a charged particle enters a magnetic field perpendicularly. So that was the formula. R is equal to mv by qb. In order to find mv, we used energy, and then we plugged in the values to get about 5.4 meters, which is approximately equal to 50 centimeters. Now, let's look at this question. A charged particle enters a magnetic field H, with its initial velocity making an angle of 45 degrees. Then the path of the particle will be. Now, before we move on to this question, this isn't exactly in meters. So we got 5.4 as the value. So when you multiply by 10, you'll get 54, so that is approximately equal to 50 centimeters. That's the answer. So, second question. Charged particle enters a magnetic field H, which its initial velocity making an angle of 45 degrees with H. Then the path of the particle will be circle, helical, straight line, circle. So let's put in the magnetic field, and in order to make our job easier, we will put this magnetic field as into the plane of the paper. So that means I draw X's around it. And then you see that we have a particle, a charged particle entering with the initial velocity, say u. And the angle at which it's entering is 45 degrees. So the condition for motion inside a magnetic field for a charged particle is that when theta is equal to 0 degrees, then the charged particle goes undisturbed. When the charged particle is entering perpendicular to the paper, perpendicularly, then the charged particle orbits a circular path. When theta is between 0 and 90 degrees, then we will have both horizontal and vertical components for initial velocity. So we will have a component u cos 45 degrees, and we'll have a perpendicular component u sine 45 degrees. So u cos theta will ensure that this particle moves horizontally. And u sine theta will give it a circular path. So we have two forces working at play. One force is pulling the particle forward, the other force is trying to spin it in a circular path. So when both of these combine together, we get a path something like this. And this is called the helical path. And that's why option B is the right option. Options A and D are incorrect because these two happen when theta is equal to 90 degrees. And a straight line happens when theta is equal to 0 degrees. Now, let's look at this question. What should be the amount of current passing through the ring of radius of 5 centimeters so that the field at the center is equal to the magnetic field of 7 into 10 raised to minus 5 Webers per meter square? So over here, we need to get the value of B as 7 into 10 raised to minus 5. And this magnetic field is due to a current I passing through a ring of radius 5 centimeters. So over here now, what we would be doing is we'll be using the formula for the magnetic field at the center of a coil carrying current. So we have a coil and we're asked to find out the magnetic field right here. We'll be finding out the current, which gives the field at the center a value of 7 into 10 raised to minus 5. So the formula is B is equal to mu naught I divided by 2 pi, mu naught I divided by 2R. Mu naught is the permeability, and it has a value of 4 pi into 10 raised to minus 7, always. So let's plug in the values. Therefore, B7 into 10 raised to minus 5 is equal to 4 pi into 10 raised to minus 7 times I divided by 2 into the radius, which is 5 into 10 raised to minus 2 meters. So now what do we do? Let's rearrange this in terms of the variable here, which is I. So therefore, the current will be equal to 7 into 10 raised to minus 5 times 2 times 5 into 10 raised to minus 2 whole divided by 4 pi into 10 raised to minus 7. So let's, multiply them together. 7 times 2 is 14. 14 times 5 is 70 into 10 raised to minus 5 minus 2. So that is 10 raised to minus 7 divided by 4 pi into 10 raised to minus 7. So 10 raised to minus 7 gets cancelled. So we have 70 by 4 pi. On dividing by 2, we'll get 35 divided by 2 pi. So let's put the value of pi as 22 by 7 for simplicity in calculation. So 35 divided by 2 into 22 by 7. So that'll be equal to 35 into 7 divided by 44. That is equal to 245 divided by 44. So this will be the amount of current. But we're asked to find it out in decimals. So we have the option. So let's look at the options first. We have 0.28 amperes, 5.57 amperes, 2.8 amperes, and none of these. So let's start dividing this. So 245 divided by 44. So 44 goes into 245 4 times. And we don't need to go further out here because when we take it as 220 and then we'll get 5 and then 2 and then 0. So we'll get another 5, another 0. So it'll be 4 again. And it goes as 4.4 amperes. So we need to find out which of these is closest, which of these is the closest value. So to 4.4, 5.57 is the closest value. So option B is the right option. So again, the reason why I'm doing this approximation is because I'm keeping the value of pi as 22 by 7, so which is kind of inaccurate. I mean, I should have used 3.14, but for calculation's sake, we've used 22 by 7. So there is some adjustment with respect to that. So option A, 0.28 amperes, option C, 2.8 amperes are incorrect. And since option B is correct, option D is also incorrect. Now let's look at the next question. A closely wound flat circular coil of 25 turns of wire has a diameter of 10 centimeters, which carries a current of 4 amperes. The magnetic field at the center of a coil will be. We have 4 options: 1.256, 1.679, 1.512 into 10 raised to minus 5, and 2.28 into 10 raised to minus 4. So how do we solve this question? So we have N as 25 turns. We have the diameter, which is 10 centimeters. That gives us a radius of 5 centimeters. And then we have current, which is equal to 4 amperes. So over here, the situation is a little bit different. We have a coil, which is circular, and it has 25 turns of the same wire. So it's kind of something like this. And we're asked to find out the magnetic field at the center of the coil. So we'll use the formula for flux density here. So flux density, that is B by N, is equal to mu naught I divided by 2R. The reason why we use mu naught I is because it's circular. So for the magnetic field at the center of a circular coil, it'll be mu naught I by 2R, but because we have multiple turns of coil, we'll put it as B by N. And we can get the value of B as mu naught I into N divided by 2R. So again, mu naught stays the same. It's 4 pi into 10 raised to minus 7. And then let's plug in the values. So the value of magnetic field will be mu naught, which is 4 pi into 10 raised to minus 7 times the current, which is 4 amperes, times N, which is 25, divided by 2 times 2 into 5. So we usually write it as into 10 raised to minus 2. So in this case, what we'll get is the magnetic field is equal to 4 pi into 10 raised to minus 7 into 100, and then divided by 2, and then into 100 again. I mean, no, it's actually 10, and then on the numerator it's 100, because 2 times 5 is 10, and 10 raised to minus 2 went to the top. So 4 pi into 10 raised to minus 7 into 10 raised to minus 1 into 10 raised to 4. So 10 raised to minus 7 minus 1 gives you minus 8. Minus 8 plus 4 gives you minus 4. So we have 4 pi into 10 raised to minus 4. So over here, it's prudent to use 3.14 because we need a value of decimal. So 3.14 times 4. 4 times 4 is 16. 1 times 4 is 4. 4 plus 1 is 5. And then 3 times 4 is 12. So we have 12.56 into 10 raised to minus 4. And let's convert it into 1.256 into 10 raised to minus 3. So therefore, using that, we got the value of the magnetic field at the center of the coil as 1.256 into 10 raised to minus 3 Tesla. Next question. A cyclotron is used to accelerate: A, positive ion; B, negative ion; C, electron; D, none of these. So let's look at each of our options. Option C, electron. Now, when we learn about cyclotron, we know that an electron is not used in a cyclotron. So option C is incorrect. The reason why is that as the velocity increases, we get a very large mass. So we have a problem in synchronization. So it cannot be synchronized properly. So that's why electrons are never used in a cyclotron. So option C is incorrect. What about option B, negative ions? Well, negative ions have more mass, and therefore they face a problem in synchronization again. So option B is incorrect. However, a cyclotron, which has AC current, can accommodate a positive ion. So option A is the right option. So since option A is correct, we can also eliminate option D, none of these. So when it comes to cyclotron usually accelerates positive ions by using AC current in order to put it in an ever-changing magnetic field. So the cyclotron accelerates at each turn, and then finally it moves out of the cyclotron with higher velocity. Now, let's look at this question. This is the final question. The magnetic field at a given point is 0.5 into 10 raised to minus 5 Weber per meter square. This field is to be annulled by a magnetic induction at the center of a circular conducting loop of radius 5 centimeters. We need to find the current required to be flown in the loop. So when it comes to this question, what they're essentially doing is they're trying to make the point 0. So since the magnetic field is already given as 0.5 into 10 raised to minus 5, we need to cancel that magnetic field by producing an equal and opposite magnetic field at the center of this loop. So therefore, the value of P will be equal to 0.5 into 10 raised to minus 5. and the radius will be equal to 5 centimeters, and we need to find the current. Again, we use the formula B is equal to mu naught I divided by 2R, the magnetic field at the center of a current carrying coil. So let's plug in the values. 0.5 into 10 raised to minus 5 is equal to 4 pi into 10 raised to minus 7 into I divided by 2 into 5 into 10 raised to minus 2. Again, over here, we just convert it in terms of the current I. So that is equal to 0.5 into 10 raised to minus 5 times 2 times 5 times 10 raised to minus 2. And the denominator will be 4 pi times 10 raised to minus 7. So what is the next step? Well, 2 times 5 will give you 10, and 10 times 0.5 will give you 5. So the value of I will be equal to 5 times 10 raised to minus 7 divided by 4 pi times 10 raised to minus 7. Both of these gets cancelled. So we have 5 divided by 4 pi. We know the value of 4 pi, right? So 5 divided by 12.56. Again, we can convert it as 500 divided by 1256. So let's divide it. So 500 divided by 1256. Again, we can't do this, so it's 0 point. So we have 5,000 now. So when we multiply 1256 by 3, we'll get 18. We'll get 18. 5 times 3 is 15. 15 plus 1 is 16. And then 2 times 3 is 6. 6 plus 1 is 7. And then we have 1 times 3 is 3. So 3768, which is the closest value to 5,000 in the multiplication table of 1256. So 0.3. And then we subtract it. 3768. So 10 times 8 is 2. 9 minus 6 is 3. 9 minus 7 is 2. And 4 minus 3 is 1. So we have 1232, which is again lesser. So we'll put a 0. So 12,320. So this is only a little bit less than 12,560, which is 1256 into 10. So we'll put the value of 9. So minus, when you multiply it by 9, so that's 1256 times 9. 12,560 minus 1256. That'll be equal to 10 minus 6 is 4. 5 minus 5 is 0. And then 5 minus 2 is 3. 2 minus 1 is 1. And 11. So minus 11,364. You'll get some value here, but that doesn't matter. We have our required quotient, which is 0.39. So the current will be equal to 0.39 amps. Now, when we have a value greater than 5 in the decimal point, then the previous digit will get converted to the next highest digit. So 0.39, because of the 9 here, we can write it as 0.4 amperes. So the value of current will be equal to 0.4 amperes, which is the same value as given in option B. So option B, 0.4 amperes, is the right answer. Again, we used the formula to be used here is the formula for the magnetic field at the center of a current carrying loop, circular loop. And the reason why is because we have to make that magnetic field 0. So we have a given magnetic field. So the magnetic field that should be induced must be equal and opposite. And so we need to find out the current required for that. And that's how you solve this question pretty easily. And that concludes this episode of NEET Preparation. We hope you found this episode interesting. For more useful and interesting content, please subscribe to our channel, which is Brain Blitz Audios. Don't forget to hit that notifications button for receiving more of our useful and interesting content and receiving the latest updates on the same. So until the next episode, take care, stay safe, bye-bye for now.